So, funny being introduced by the man himself. Alex did so much for the local Rust community, and would really like to thank him for that. Okay, so hello everyone. So I'm going to present Ferrocene and about Rust in safety critical systems, and also talk a little bit about what that is and demystify that a little. So who am I? I am Florian Gilcher. I'm the managing director of Ferrosystems GmbH. I was previously in the Rust community and core team. I am a co-founder of the Rust Foundation, and previously I've done data center operations to my previous company, which might be relevant for this talk. So at a glance, the company was founded in 2018. And I've been providing Rust training since 2015. And the whole company has, we always joke, we have a collective amount of 100 years of Rust experience. And we're mostly a services business and tool provider. And that's the part of this talk, we have the first to qualify a Rust compiler called Ferrocene for ISO 262 and IEC 61508. I'm going a little bit into detail what that is. We employ 10 project members, past and present, mostly in the infrastructure and quality management teams, provide and maintain several Rust tools and initiatives, particularly if you've used Rust Analyzer, that's being hosted in our company. And it's been, thank you, always been a great pleasure to work with the Rust project there. So, before we get into the topic, this is a question that has been grinding my gears very fundamentally. Why is Rust successful? Because it's pretty cheap to invent programming languages. We have around 9,000 of them. Most of them don't make it. And I think it comes down to actually bold mission statements and actually delivering on them. So Rust still says we are a language empowering everyone to build reliable and efficient software. And I think that's pretty interesting if we talk about safety, because this is already a very safety-minded statement, but it says everyone should be able to build high-quality software that is highly reliable. And I think the first question we have to ask ourselves, if we think about the success of something, is, do we even have a problem here? Because when we're talking about a new programming language, we're asking people to knock down their houses and build upon a new house on those foundations. Moving the needle isn't quite enough here, because if I were to incrementally move in the space of programming languages, I could probably just use a linter or a small tool. So why did people invent Rust? And actually, the first talk I've seen about Rust in Munich was by this gentleman there, Alex Crichton. And he had this slide where he said, well, there's this continuum between control and safety, and people say control, low level, means it's unsafe. While if you're highly safe, we're giving up control. And the question was, can we put something, like, can we just move off that continuum and just step off? It's quite literally the quote, can we just step off? And I found that very impressive to say. And that convinced me that there's something more than just, well, we are inventing a programming language there. No, we're addressing a problem. Next question, everyone's talking about Rust memory safety. So that's the thing everyone says. The White House is writing about it. All the security groups are writing about it. But if we look at the early large adopters of Rust, they've already been using memory safety safe programming languages at a lot of places. And to be honest, if you look at it, they have been using Rust also to address other problems. For example, the control problem. Like we're already using Java, but Java is unpredictable, uses a lot of resources, uses a lot of energy. Maybe something else would be useful. And we see nowadays, particularly in our training business, quite a lot of companies using Rust much more Java-like, which is interesting for a language that is a systems programming language. But we're also seeing people using Rust on microcontrollers, just the same. And if we see how Java has struggled in the 90s to basically bridge that gap, being the language that works in microcontrollers with small additions in Java like that, I think that's a pretty interesting thing to observe. And I think that's not the whole problem. So Rust addresses many other things behind memory safety. It is actually a language that encodes encapsulation in its type system quite well through its module system. It is a pretty strict language. It comes with other languages that are also stricter. It does not, the Rust compiler does not do a lot of error correction. It gives good errors on what you're doing wrong, but it does not do any work for you to make your programs correct. It does not try to sense out what you do. It is surprisingly strict. It has advanced functional features that enable classic functional programming things like making illegal programming states just irrepresentable. You cannot ever even run into them. Then it has great features for asynchronous parallel programming, which was kind of a good thing that we could address that. So Rust allows to spend development capacity on higher level problems than memory safety. To get a little bit into like some receipts for those claims, there's an interesting paper about programming language adoption, empirical analysis of programming language adoption, written in 2013, Majerovic and Ariel Robkin. One of the problems I have in general is that there is not enough research about this. A lot of claims about how programming languages are adopted and how they're taught is a lot of the discussions are vague, but the people who are doing research in that area have pretty interesting findings. So I wish there was more of that. Particularly one of the interesting things here is, and to me, as someone who was part of the community team, this isn't surprising. One of the core claims here is programming language adoption is a social process. Emotions towards features are much more important than any kind of rational view. And popularity is actually a very important factor in adoption. But the more interesting claim of this paper back in 2013 was static typing and correctness were not in the value set of the respondent group. They were absolutely not interested in that. And if you think back, 2013 was the time when AWS finally had breakthrough times, like all the hyperscalers came up. They had other problems. They needed to code very fast, get all of their software as a service systems up and all of these kind of things. Now, how does Rust, that came out in 2015, become... So first of all, that explains why other languages that try to address these problems weren't successful. Second, why did Rust suddenly become successful, and also languages out of the same generation like Swift? And I think it's down to that. Anyone knows who said this? Move fast and break things. Mark Zuckerberg. Perfect. Thank you. Who said this? No, also Mark Zuckerberg. This is actually the actual engineering credo of Facebook since 2014, same year. They've moved past this, and they've moved past this a decade ago. Everyone's still quoting the first one, but no one's quoting the second one. And this is the explanation. We've had a value shift. People suddenly care about their systems not breaking all the time. That was permissible for a time, but yeah. So we actually have a pretty modern software challenge. And that is two things. Correctness at large. We're building huge systems nowadays. We cannot have all the small components having tiny and subtle bugs all the time that interfere with each other and break each other. And the second is correctness in motion. All of those pieces are being built independently, and we need to make sure that they don't break each other during the development process. This is where the need for strictness comes from. I've seen an amazing talk a couple of months ago where someone was saying this is basically the problem you have on a smartphone nowadays. You have the operating system that gets patched, well, every year. It has a major release every year. And then you have the applications on top, and it is a completely legitimate customer demand that their applications don't break all the time. And their conclusion in that talk was the C ABI is too weak to express that boundary well, and they frequently run into subtle bugs where they thought they didn't break ABI, but they actually did. So this is a pretty interesting observation that correctness becomes a much broader problem. Which brings me to the topic of SDV. SDV, as any industrial term, particularly in IT, is ill-defined. I'll make a very short one. SDV is software-defined vehicle. That is currently all the rage and all the push in the automotive space. And but certain components that people agree upon is cars and other vehicles, also planes, all of these become more and more defined by software. We could even include the small robots that run around here. Today was actually the first day where I held the elevator open for a robot. It's both on the car and the services they interact with. So we have connected vehicles. Every vehicle that you buy nowadays has a SIM card and calls back to some cloud services. And that whole thing ceases to be immutable. We're talking about apps in our car. Some of those approaches are good, some of those approaches are bad. I think the first problem people ran into were thinking about turning cars into smartphones and then figuring out that cars are not smartphones. They have wheels, smartphones don't. So essentially what you have here is, so what is SDV? I can see this. So when you have these, if you go to any kind of SDV conference, you see two styles of talks, either by an automotive supplier, and it has a pretty big car down here, which runs all kinds of services, has a hypervisor to separate all of these things, and then you have a little cloud somewhere, and it says cloud services over there. If the talk is by any of the hyperscalers, it looks different. The car is pretty small. It runs Kubernetes and not a hypervisor. And there's a lot of services up there. So also this whole interpretation very much comes out of, like, you see these two industries clashing together very hard, and everyone mostly thinks in their context. But how is that an interesting space? So connected vehicles have issues they didn't have before. They have a massive code size increase in all of their components and in total. So the components are getting larger, and the whole code base gets larger. We now have a flexible, complex system in constant rearrangement. Google may shut down one of your services without notice in 2 months, and then your whole fleet has problems. But security concerns are on the rise. Suddenly, cars that were not connected to the internet are suddenly connected to the internet, and most of the software that is built for them is actually not built for security. It is built for what is called functional safety, and that's two different things. And that are sometimes at odds with each other. And also, because the car industry does very good grading on how impactful a system is, you have many diverse systems in the car of different criticality, both in the cloud and in the car. Hopefully, your engine won't shut off if the connection to your cloud system's gone down, but you need to make sure of that. So the cloud system should probably not be as critical as your engine control. That's what I mean by different criticality. And then this whole idea of reuse comes up. It used to be that all of those systems, because they were small, would just be built and rebuilt all the time, and that was fine. This is not now, with the current code sizes, not possible anymore. So suddenly we need to have systems that, live over years and even decades and stay stable. So Rust is actually being adopted in this space, particularly cloud first, moving into the car. I think that's more a question of ease. Using Rust in server class systems is a well understood easy to make problem. This is a good starting point for a company that wants to adopt a new programming language, something where they don't have to reinvent everything in the beginning. Non-safety related use cases. First, places where you cannot do any harm, like physical harm. And interestingly, big systems first, smaller systems later, just again, because of the reason that this is a well understood space. The other thing is usually with a strong eye on security first. So the entry point for Rust is security. Safety comes later. It tackles the security problems of that industry, and then people tackle the safety issues later. I'll come to the difference there in a second. So the safety comes out of need. So the security comes out of need, and then the safety comes the same out of the need because the industry relies on that happen. So I'd like to talk about a few initiatives in Rust there to give an overview and just like make them a little bit more accessible, particularly to the people who are not usually in that space. So Rust in the automotive space is new, and we've currently find 4 kinds of initiatives. Qualification, I'll get into that in detail. Open source initiatives, like the Eclipse Software Defined Vehicle Group, industry collaboration efforts in general, and actual standards writing. So what is functional safety? The objective of functional safety is freedom from unacceptable risk of physical injury or of damage to the health of people, either directly or indirectly. So whenever I connect software to a physical component, like for example, one of the robots out there, I want to make sure that they don't give someone a slap in the face, but they actually touch them nicely. So do no harm. And that is a set of practices to ensure highly reliable systems that avoid harm, in particular to human beings. They're defined in several standards with different criticality levels. So some classic ones is IEC 61508, industry standard in industrial machinery, ISO 26262, automotive, a couple one for medical, railway, and avionics. Usually they're all subsets of each other. For example, the ISO 26262 is actually built on top of the IEC 61508. It is built out of it. So the industry one came first, and then it was tuned towards automotive. The standards, and that's the interesting one, do not only include software, but whole systems of software and hardware. There's, for example, also one for earth-moving machinery. And one of the differences there, for example, is not in the software parts, but in the hardware parts. The difference is a car runs for 1 hour a day. A tractor often runs for 8 hours a day, and that has very different demands on the physical components. They get hotter and all of these kind of things. But on the software side, they're surprisingly similar, except for the avionics standard, because avionics does everything differently. But the interesting thing about those standards is they're rarely prescriptive. They leave quite some liberty. So what they provide you with is, here's an objective. You need to rule out the following thing. And then it is up to you to make an argument on how you fulfill that objective. And then there's this whole thing with assessors coming in. So you usually have a third party that then looks at your argumentation and says, yep, we follow your argumentation. We think you've made a good effort to actually make these things safe. And a lot of that comes actually with willingness to accept liability if you break the things that you've promised. So to give you an example here, this is from the ISO 26262, and from the software part. And for example, here, Rule 1A says enforcement of low complexity. That's not like that's a programming practice, but how you enforce low complexity, I could on the spot come up with 10 different ways of doing it. Could use Clippy cyclomatic complexity and say this is enough, but cyclomatic complexity does not say a lot about your architecture. It says things like use of language subsets, and that's always the question, where do I need them and what kind of subset would I need? But we also already see this in Rust. For example, kernel programming in Rust is usually done without any floats. That could be a subset. And we have something like enforcement of strong typing. That is something that if we use Rust, we can check off very quickly because Rust is strongly typed. Thank you very much. That was a good idea. And it's also sometimes surprisingly specific then. So for example, down there, there's use the default in switch cases to detect an error, which also hints to they're thinking about C and C++, because this is very clearly a C feature that they're highlighting here. So they give you quite some liberty. That was the wrong way. And the other thing is those standards are also cultural. So practice preserved as necessary is sometimes actually not mandated by any standard. And this leads to many misunderstandings on many sides. This has been something I've been dealing with for the last 3 years, telling the Rust project that what other people tell them is actually not correct. So for example, things like programming languages used in functional safety need to be ISO standardized. This was the first question I asked my assessor. Do we actually need an ISO standard? And they were like, no, why? So, but you see this around, like we've seen this around for years from the side of the Rust project, that people were criticizing us that we don't have an ISO standard. We don't need one for this, like at least not for this. ISO standards can make sense, but not for this. Or there can't be any safety qualified open source products. That was just something that people believed, because there's literally, I'm aware of 2 of them. One of them is mine nowadays, but it's coming up. And the other thing is, standards care about imperfect software, and I think that's good. So they want software to be of high quality, but they also appreciate that if it isn't, its defects and deficiencies should be known. It is okay for the Rust compiler to have a bug. It is very useful if we actually know where that bug is. And the Rust project actually, so there's always the criticism of the Rust project of it has over 5,000 open bugs. And from our perspective, that was really, really good, because a lot of the bugs in the Rust compiler are at least well known and well documented. This is an awesome piece of work. It is totally okay that in something as massive as the Rust compiler, there are things that don't work correctly. So there are standards that, or all standards actually assume that your compiler has bugs. And that is also not important. Important is that the thing that in the end triggers your break works correctly. So it's about how do we make sure that we use that we don't run into any issues when using the compiler to build a braking system that actually breaks correctly. So we prefer the bug we know over theoretical perfection. That's quite different from what academia does, so it's often not an academic problem, which is fine. Like if you can rule something out completely in a theoretical sense, safety people will say, oh, that's great, let's do that. But you can't do this on a daily basis. It is actually extremely hard work to make these things work. And then there's this other thing. Does safety mean keeping things stable? A classic practice in safety is actually forking a tool, adding changes, fixes, and documentation, making that error list, and then keeping it stable for as long as possible. I know about a system that is still developed against a C compiler from the 90s with a 250 pages bug list that just says, don't do this. And the engineer that I talked with said, we're not programming C, we're programming the language this compiler implements. And that can be feasible if you have a very small system, but that leads to outdated software that's stable, but also has a lot of bugs to work around. And this immediately collides with the problem that we have nowadays, because security needs fast patching. So we're seeing a collision behind that with this practice of functional safety that is slowly evolving and very deliberate, and security that is all about finding the holes that still exist and breaking in. So we need faster updates. So we need to move faster while keeping things safe. And the other problem here is these practices are not well understood outside of that community, because it is often happening behind closed doors. So there's nowhere to go if you actually want to look at how does this material that I talked about look like. So, the currencies of safety critical. So in safety critical, we have requirements, our external and self-imposed objectives on a piece of that a piece of code needs to meet. We have activities that we plan to reach a certain level of quality, some mandated, some self-imposed, and we need evidences to provide that those. We need to provide evidence that we actually met those objectives. Yeah, and I'd actually like to go through that on Ferrocene. So Ferrocene is a safety critical downstream of the main Rust compiler that never loses track, but is still ISO 262 and IEC 61508 qualified. We're currently working on the standard for medical software. And it is, and that's interesting, non-invasive. We don't change the compiler. If we feel like there's any compiler changes needed, they go actually into the Rust compiler because we want the Rust compiler to be the safest Rust compiler. What we add is all of this documentation to provide those evidences, and we actually use the same license of rustlang/rust. So one of those two projects that I mentioned that are open source and safety qualified is actually ours. And it actually also uses the same test suite as the main compiler. So what we've done here is a process called tool qualification. So in tool qualification, you make sure that a tool is readily vetted for use in safety critical. That is not mandatory, just allows users to later say, okay, someone looked at the compiler for us already, so we can look at the artifact. So this is the idea behind tool qualification. It's a service that you can do before the actual development of the software happens. And it is an exercise in gathering knowledge about the tool. And for us, we wanted to have that as fast as possible and as up-to-date as possible. So let us inspect one of those arguments in practice, so that this isn't just a theoretical talk about how safety works. So let's inspect the argument. The Rust language implementation of Rust C is heavily covered with tests. And the first thing we do, and you can look at all of those documents if you want to read along on public-docs.ferrocene.dev, because all of that material is open, because precisely the problem is I want people to understand more of how that works and demystify that. So all of that material is open. So what you do in this place is, first of all, you come up with a plan. So we have an evaluation plan, which is how do we figure out what is even necessary? So what are the things that need addressing, and a qualification plan on how do we do the actual qualification. And both of these end up in two other documents, which are the reports about both of those activities. So evaluation is we look closely at the Rust compiler. How does it work? How does it call into a linker? Where could faults be injected? So for example, if we're calling the linker wrong, things like that. Or if people use certain linker flags that break Rust. It's all possible. So now the Rust language implementation in that sentence. So what are the requirements for a Rust language? Yeah, we probably need that. That sounds like a language specification. And when we started that project, Rust famously had no specification. Still hasn't any. So this is how we came up with the Ferrocene language specification. And to be honest, we bike-shedded about the name language specification for quite long, because one of the problems here is if you write a specification on how a compiler works, one of the problems is if we were to come out with a specification just like that, it didn't communicate well, people would assume that would be a officially blessed one. It's actually not the case. We wrote one for ourselves. The most important thing is it has a pretty interesting feature that differs it from the C specifications. Every sentence in that specification is addressable. So all of those small parts are hyperlinks. And what we then do is we do something called tracing. So we go through the whole specification, and you can see here, this is the link name. And it's pretty interesting, the garbage of characters you see. is actually also encoding, it's a signature of the actual writing. So if we change the writing, this will change. And then we link all the tests, the test constants, 690 tests here. That was a massive amount of, okay, this test tests this test tests that, and so on and so forth. And then we actually make sure that we put this in classic Rust, we just put this into the build system. So we extend the Rust build system to not only run all the tests, but also run this thing called, build this thing called a traceability matrix. And this tracing fails if a test was added that has no specification attributed to it. This will probably happen now that we start qualifying Rust 1.8.2 because it has added a lot of language features. That means there are now tests where there's no specification section for. So our specification is out of date. Someone's testing something that we're not aware of. So this idea is bidirectional. Or the other thing is we add something to the spec and the traceability matrix will say, hey, but where are the tests for it? So we can actually figure out if language features are well tested. And in the end, and this is where the formalism comes back, we make something called an acceptability statement. So all of this work boils down to, this is our final argument to the assessor. It is, hey, by the way, we've done all of these things, particularly we've done requirement traceability, and we have a test results overview, and we think that has been reviewed, and this is demonstrated compliant with automotive standard ISO 26662 and IEC 61508. And then you do a couple of rounds with your assessor where they disagree with that statement. For example, one of the things we had to add in that situation was a better list of known unsafe, known undefined behavior and things like that. And in the end, that passes. It's actually a pretty structured and interesting process that I would love if more people would at least be in the thinking that this is actually a simple process that you can apply even for yourself. Maybe not in that formalism, but it's actually interesting that there are lightweight safety processes that are quite pragmatic. So in the end, you get a stamp for that. Here we go. Ferrocene is accepted as a safety critical open source product. So the current state, we're releasing every 3 months. So we're one of the fastest products on the market, usually lagging by the main compiler by a cycle. In November, we will have Rust C 181 qualified. It comes with support for targets that are not supported by upstream. So for example, QNX, which keeps load of the Rust project to test these highly specific things. So we can still feed problems back into the Rust project and say, hey, by the way, this is where the issue showed up. And interestingly, because of that, we have a parallel build infrastructure to the Rust project that has been used, for example, for RISE. They wanted to get RISC-V up to tier 1 in the main project, and we were able to say, okay, you can do this on our infrastructure, like you can do all the busy work and then offer that to the Rust project. If the Rust project doesn't accept it, there's still the possibility that we just test it downstream. So this is actually an option we now have even for non-safety critical cases. We can do quality assurance for targets where the Rust project doesn't want that. And in the end, it frequently finds issues. And I think this is the most important thing. If these processes don't start finding issues, they're not worth it. So here's a bit of a list of things we fixed. Lots of problems with licensing, by the way. And like all of these things, we didn't find anything nefarious or huge. It's mostly polishing in the corners, but that's also good. So a huge amount of miscellaneous fixes. The bootstrapping system became better. We added structured output to the build system to then consume it and all of these kinds of things. And I think this is a very nice thing for the Rust project. But as you've seen, we've basically extended the software quality measures of the Rust project. We have not invented our own, which also means the methods of the Rust project are fundamentally capable of building software for high criticality. I've been in a talk with a safety assessor where in the Q&A he said, I don't understand how some people do this as a hobby while I have to force my engineers to do it. it has also proven that SSs have absolutely no issue with open source software, even externally built software, as long as you get that process right, and particularly as long as the upstream project actually has a high quality standard. And I think that's a difference. There's the impression that open source is somehow like going along and just doing things. That's not actually true. And we have qualified the whole Rust language for usage in safety critical, requiring no language subsetting. It might still be useful for on a project to project basis to avoid certain features, but that is something that is not safety related. That is actually common practice. Again, coming back to if you're building a kernel, you probably want to practice a little bit of a different Rust than others. And so maybe you write down how you practice Rust. So good Rust practice, I would actually like to come to a point where we're talking about good Rust practice, not about good Rust safety and good Rust security practice, because I think they're very fast becoming the same. So, to start finishing my talk, I'd like to still highlight a couple of initiatives where maybe if you want to drop by, you can you can even be engaged in this and have a little bit of a feel for that. Particularly, a lot of things are happening in the Eclipse SDV, particularly in the so-called Rust Special Interest Group. Eclipse has a whole project for software-defined vehicle open source software. Actually, Peter Levasseur over there is one of the also involved in that SIG. And what we want to work on is, for example, things like common code style, common processes, particularly in testing, which is much more like teaching people about how Rust tests, and that there's a lot of commonality in that. An exchange place for experience and certification. This is really just for the certifiers. But also we see there's a lot of misunderstanding about Rust itself. And that's also a good place where maybe some people who are more experienced in Rust can help. So for example, by dropping by, giving a talk, things like that. And obviously we also just want to engage with other parties such as the Rust Foundation. The Rust Foundation also has a safety working group. And this group intends to advise the Rust project on the needs of safety critical systems of all kinds. So that a little bit of that whole mess of that discussion and how it applies to Rust is contained to that group. And after that discussion has happened, we can actually do proper recommendation to the Rust project. And also here, creating and engaging with efforts to create coding guidelines. One of the biggest parts we see is Rust Unsafe still has no good written guidelines. And actually also advising the Rust Foundation and other parties on how specification efforts work. An interesting observation, coming back to my point, members of the safety working group are not just safety-related companies. We are now seeing Apple, Adobe, and so on and so forth. If I go to safety conferences, we see a lot of the classic FAANG companies actually sending someone just to see if there's a good software practice to be found. I always say good software practice can be found anywhere. Just avoid not picking up the bad ones. And there's also a standard being written for 2 years now for coding standards in the SAE, which is similar initiative similar to ISO. If you're ever interested in looking into that, joining it is free and you get access to the documents. And that's a general Rust coding standard that informs people on how the Rust toolchain can and should be used, for example, in automotive. So, current issues, just quickly. There's a number of initiatives forming around Rust that's hard to cover. Like they pop up left and right currently, leading to friction, confusion, and then the Rust environment itself also isn't simple, I have to say, which is no complaint. It's just like this is the state it is. And the other problem is many initiatives in safety are planned but need to be executed. The problem is it's a space where investment, like if you actually want to, like this whole qualification wasn't inexpensive. And so the problem there is these efforts often come in pretty big chunks that you need to argue for. So there's more initiatives planned than are actually executed. So it's not very agile, not very rolling. And then there's the problem of hastily applying industry practice, like, for example, strong language subsetting. So I was in the first meeting of SAEJ 2020, the first thing I needed to tell the people from Israel is like the language does not need subsetting to be memory safe. This is actually the goal of the language. It is memory safe in and by itself. Everything else is a bug. Please report it and don't write a standard around that bug. Report it. So this is actually people in safety are not quite used to. There's people on the other side that actually care about the correctness as much as they do. And there's a widely differing knowledge state. Like this exposes that there's people who want to have their problems addressed, but they don't know enough about Rust or their environment. The other side is the same. Like people in the Rust project don't know enough about safety, which I'd love to change by not only me being the person on stage that talks about these things, but also other people, because this has been something that I've been trying to tell the safety industry. If you want the Rust project to care about your things, show up. But there's a couple of very legitimate issues. We are late on delivering a language spec. Very late, far too late. And that actually leads to the point where our specification is being adopted as the specification because people are starting to write tools on top of that. So we are at the state where there's a demand for qualified tools, and with nothing else available, people are using our thing. And that leads to a certain friction. Lack of consistent guidelines is a really, really huge problem. We had a chat about this yesterday. Rust actually has 5 different guidelines in the main project. And, 4. And then there's one external. And so figuring out what is actually true, because they have different opinions on the same facts. As simple as, what is the actual slice layout? Is it undefined? Is it this? Is it that? And there's lots of knowledge in heads that needs to be written down, which also speaks to spec. And finally, the whole problem of we're still talking about 2 very different software communities that got kind of split at birth. So one of them is for Mars, others, so cloud programmers are from Mars, safety programmers are from Venus. That is actually also okay, but appreciating that very head first and saying, hey, by the way, let's find the parts where we can find goods exchanges important. Because in the end, I think what we're all talking about is correctness. And I think the SDV space, and this is why I like being in it, is one where that is being tackled head first because of all of those things coming together. So scale-focused companies are currently learning a lot about correctness, and I think they could learn a lot from the good practice in the safety critical space. As every industry, there's also a lot of malpractice. And correctness-focused languages, they have to learn how to scale these things. And I think the Rust project has been incredibly good at scaling correctness. I think this is underappreciated. Like the whole quality assurance machinery of Rust is not only industrial grade, but amazingly great. And Rust has deliberately moved itself into a space where it's saying, hey, by the way, let's be productive and correct and reliable. Like everyone should build reliable and efficient software. And I think that's a good claim. And that's where I think we should make all of these development practices less special and start throwing all of those experiences into a pot. Thank you very much.